Excellent, excellent, good. Well, welcome everybody. Let's make a bit of a start then. Welcome to this evening's Whitechapel lecture. This is our occasional series of lectures that the Founders Company offers out to anyone who's interested. Delighted that we've got a good attendance tonight. We are recording it as well, so if you've got friends and colleagues who've missed it, then obviously you'll be able to share the recording with them afterwards. I'm really pleased that tonight's lecturer we have Anthony Evans. Anthony is works for his own company, ABL Innovations Limited, but also he has been working in and around the industry, the castings industry in the UK for many years, and currently he's the Institute of Cast Metals Engineers National President. So the Institute of Cast Metals Engineers is the professional body for individuals in the castings industry in the UK. Now, tonight he's going to be talking to us about digital twins, which are virtual models of a physical object. So I would remind you that we're recording tonight's presentation. If you have if you have trouble with bandwidth, then sometimes turning the video off is helpful. I'd perhaps ask everyone to remain on mute while Anthony is speaking. You can use the sort of chat function as well to ask questions, but also we'll have a bit of a Q&A session at the end, which will turn the mics on and people can ask questions as well. But say in the meantime, if you've got questions, you're welcome to use the chat function as well. So I think without further ado, Anthony will introduce himself and start sharing his slides. And over to you, Anthony.
Brilliant. Thank you very much, Pam. If you can get this working. Okay, is that sharing okay, Pam?
Yes, it is.
Brilliant. Okay. Yeah, Pam, thank you very much for the introduction. Just a little bit more about myself. As Pam says, I've been in the aluminium side of the industry for 30 plus years now. Stranger, I graduated from South Wales and Cardiff and Pontypridd, and my first placement was an aluminium wheel foundry in Treforest. And ever since that placement, I've never left the aluminium industry. So I'm working within UK PLC and then going across towards the SMEs. Had the opportunity to work on a number of different programs, both in terms of low pressure die casting, high pressure die casting, gravity, and more recently in terms of sand. Another advantage of working for the PLCs was working overseas, and I did have a great opportunity to work for a number of years with a foundry, particularly in China, but also in terms of India, and then more recently, as of this year, equally working with a high pressure die caster who I've previously worked with as a Taiwanese owned foundry, who are now operating out of the Philippines. So it's just a little bit more. So this evening, going to try to talk to you about an exceptionally fast-moving and wide-ranging advancement within our industry, and hopefully an appreciation of how it can impact various aspects. Hopefully, I'll be able to give you some ideas of how we can also better position ourselves, in my belief, for the industry and the opportunities that I believe that we have going forward for us. The main focus will relate to digital twins and how they're being successfully utilized in two completely different separate factors and fields, but I've tried to link two examples together which relate to the same aluminium high pressure die cast components. So as Pam rightly said, a digital twin is just a virtual replica of a model. It can be a physical object, a system, or a process. It's probably quite easy to appreciate if you think about Deming's principles of plan, do, check, and act, where within a digital twin, the do and the check are still completed, but they're completed in a virtual world as opposed to the real world. And in terms of therefore simulating what its counterpart could be in, let's call it, the real world. Just a little bit more in terms of the twins. So the twins, it uses data. The data can be collected from sensors, from historic data. More recently, it's associated with algorithms, particularly associated with casting simulations. And therefore, it's replicating physical behaviors and characteristics, but as I said, in a digital environment. The other side of the twins also enable real-time monitoring and informed decision-making processes, and particularly when it comes to managing operations, viewing operations, and hopefully you'll see as we're going through in terms of a much more of a global footprint. So the two areas that I thought it would be useful to have a look into is firstly in terms of the component designs and how the digital twin can change the way component designs are not only created, but the outputs from those twins, where quite typically now it's known that in the automotive sector that the old method of crash management and crash simulations of vehicles is dramatically reduced because it is programmed and predicted in terms of a digital mode. The other sector that I'm going to try to look into in a bit more detail is in terms of manufacturing. So particularly in terms of manufacturing areas, it's how we're able to simulate manufacturing processes to therefore optimize the production which could be achieved, aiming to reduce the downtime, and obviously to be able to predict in a much more controlled fashion product quality which the individual cells will be able to produce from. So as I said, the first area we'll look into is in terms of the component designs. Just looking, first of all, in terms of the sort of conventional way that components have been designed. And again, I'd just like to stress I am specifically talking about the aluminium sector and predominantly automotive. So generally speaking, the customer will initially, they will work on their own design concept. They'll create CAD around that design concept. Probably they will come to a decision in terms of their design and take it through to FE analysis. So at that point, they're probably quite entrenched in terms of the design in which they need to follow. The normal path then would be that it would be passed across to the foundry, where the foundry would complete its casting simulations. But quite frequently, it just wouldn't stop there. You would have a continuous loop going backwards and forwards between the foundry and the customer. So the foundry would obviously want to change things to add draft angles and feeders in certain areas to optimize the actual component itself, which then needs to go back to the customer, which then needs to go back through CAD reconcept, back through FE analysis. But then more frequently after that, even when the foundry and the customer have completed their loops, it would then go to both in terms of the tool makers and particularly in terms of the machine shops who would also want to make their own changes, and then more optimization. So again, it would go through that almost a continual design change back, always converting back to CAD, always going forward in the CAD onto the next person in the supply chain, requesting changes in the CAD, or quite frequently modifying the CAD themselves, and then send it back through. This concept is typically designed as is referred to as design silos. So everybody working independently. A big negative is design harmonization. So when you're in these design silos, quite frequently the design keeps going back to the way that we've done it before, and always reverting back to the past. And typically, it wouldn't be unheard of to experience lead times in excess of, or certainly up to 1 year. And that is quite typically from when the design was initiated by the initial customer. It's gone through all of the foundry processes, all of the tool making and machining design iterations and changes, back up to the customer for a finalized CAD, a rerun through in terms of the FE analysis, and back through the supply chain. So it was really was quite a lengthy time period. Today's components are very different. So the majority of components which are used in the automotive industry are from a topological based design. They've normally had an artificial intelligence interface which has already optimized the design themselves. This vehicle platform, this is the Tesla platform, and this platform has taken probably in excess of 30 individual aluminium die castings, which previously would have been bonded, probably not welded, but or joined together, and has driven it down to 3 individual, very large, as I said, topological based design components. So therefore, based around these changes and the fact that the EV market sector does work at a much faster pace than the traditional automotive design factors, an alternative approach was needed to be created. So now look into how some people within the sector have managed to overcome this. So in terms of a technique, and the technique which I'm been able to work with more recently, is associated with subdivisional modeling. And this was originally utilized in the computer graphics and the games industries for animations and movies, where these subdivision bodies are comprised of vertices, edges and faces, which form a mesh of polygons. But using the algorithmic subdivides within the mesh, they're able to create a much smoother tangential and continuous surface. So therefore the edge pyramid from a low polygon will counter transform into a smoother organic shaped object. As I said, and these are concepts which started in the games industry, moved into movies, and now come in terms of automotive, and is now much more readily accepted as a concept in the CAD world. It is interesting to note that this technology within CAD has been implemented in CAD tools for many years, and therefore the CAD systems have generally not had any concerns or issues in terms of the integration of this method of subdivisional modeling into customers' CAD systems. So this is a typical example of a topological optimized component. Again, an aluminium die casting, obviously automotive, and obviously a very large component. And I'll try to walk you through how this company, Bionic Mesh, work with topology and work within the CAE modes. So just stepping through, they will create the base subsurfaces. They will add the flanges onto the designs themselves. And then start to look in it in terms of the mounts and the solids which will be fixed into the end designs. Obviously adding ribs as is required in terms of the strengthenings. And all of that work has been completed, and this is a real example. All of that work has been completed within 2 hours. The most important thing to recognize, though, that all of that work has been completed within CAE. So when I looked at those silos to start with, all of that work has been completed in the first silo in terms of the CAE and the FE. It's never been worked on in terms of CAD. And it will always be created solely in that mode there, and they will only create the CAD right at the very last moments. But the same goes in terms of the new way of doing the FE. So in terms of the crash management techniques, in terms of the stiffness, the MVH, and fatigue, this is again all managed within the CAE side of things. Therefore, because it doesn't go from CAE into CAD and then back to CAE, it's fully optimized within the CAE function. Everything is added, so everything which is normally associated with what the foundries would do in terms of the casting optimization, in terms of the draft angles, and etc. That is again added, and that is being able to be added because this system is so linked to the casting simulation packages which have been previously run, and as I said, using the algorithms to pull back into this level of CAE. But again, it is a proven case study that again it took a further 2 hours just to complete this level of FE analysis using the techniques that they have available to them. So they use this technique does use it's a completely different approach to the development of castings for the vehicle structures. It is a technique which doesn't follow the traditional sequential approach to component development, taking the customer's CAD through to CAD and CAE loops. So this fully CAE driven process, in which the design requires virtually no CAD support and detailed production ready CAD, is only generated at the very end of the design cycles. It has massively reduced the lead time in terms of what these suppliers can offer to their automotive customer base. The second sector that I'd like to look at in terms of the digital twins is associated to the manufacturing processes. And most of these, well, the components that we just looked at are high pressure die cast components. So most of us are aware that high pressure die casting it's a really complex manufacturing process. It requires very large tonnage of machines to be able to produce these components, and the level of controls associated with all of the other associated processes in terms of trimming or quenching, the automation to extract the components, to spray the dies. High pressure die casting is renowned for making very fast components, very thin wall components, and components absolutely exactly to net shape. It has possibly always had a bit of a historical issue associated with product quality in terms of downtime and also quality concerns. But it is a part of our industry, certainly in terms of the aluminium industry, which has always stepped up and has always continually tried to improve what it can offer in terms of its processes and in terms of the level of improvements that can be made in terms of the materials within the die casting processes themselves. So in terms of looking at a digital twin associated with high pressure die casting, typically a high pressure die cast twin will require at least 100, probably more, associated with 120 or 130 individual data inputs, which will feed back into the digital twin. Just picking on just an absolute handful of what those data inputs could be. They will obviously all be associated with energy, but that's not only the latent energy required within the machines. The die casting around the world, in terms of humidity, atmospheric pressures, it can all have a huge difference in terms of the casting output. In terms of alloy performance, density measurements, the number of data inputs which could be associated with that element could be quite numerous. And then you've got all the basic fluid and process control and condition monitoring type of normal data outputs from the cells and inputs into the digital twins. So, like I said, it's probably the most complex and challenging area within die casting to actually be associated with digital twin. But as I said, this sector is very much renowned for rising to that challenge and seeing what opportunities can be developed for their processes and continual improving their equipment bases. In terms of digitalisation, so this is just a replica of a digitalisation, and then what I'd hope you'll be able to see is within this digitalisation how each of those individual data inputs that we spoke about, probably 100, 120, all of those will be outputs from this digitalisation, but are inputs from the real world. So this is not one of Beulah's largest die casting cells, but it is a 9,000 ton die casting machine. So it is a very large die casting cell. the component that is being simulated as manufactured there is very similar to the rear of the Tesla image that we saw a little bit earlier. Okay. So if we think about high pressure die casting and in terms of the digital twin, the main benefit is in terms of global manufacture and in terms of the remote access, which would then be available for performance data and quality. And although that has always been available based on terms of production output and in terms of video capture, the digital twin is then able to predict what would be happening from the cells and relate back to that performance data, which is actually achieved by each of the individual global platforms. As I say, it's be fully interactive. It would be back to that real-time viewer type of example that we've just looked at. Obviously, everything is available in terms of real-time measurement, but the most important thing is it's not only a recording tool now, it's actually a tool which you can actually affect the casting process wherever you would be positioned around the world. It's also then taken as a much bigger step forward to create the ability for AI decision making associated with fully autonomous production. I think we could all appreciate if the customers need to have their individual machines much closer, if not on the site of the individual car manufacturing plants. Because of the size of these components, they're not able to be shipped around the world. So there's much more of these large die casting cells remotely associated around the world. The digital twinning is giving the control and the ability to predict what will be able to come, what will come out from the actual casting process. But as I said, it really is taking us much more into a world closer to AI decision making, and in terms of what really we should be changing on a daily basis associated with the production. So then just trying to have a think about what's next. For me, the what next is really associated with Industry 4.0. We've touched on what is remote in terms of the remote access. The big advantage of high pressure die casting machines is their connectivity, which is available for all of the machines wherever they are. The real-time measurement and therefore the retrospective analysis using the big data type of techniques. But then if you think about it, that lends itself to IoT-based decision making about self-management, optimization for performance and in terms of quality, and say starting to really close down in terms of a a true Industry 4.0 process. Finally, then, it would be the integration and the ability to monitor and to enhance the casting process. Obviously, energy consumption and reduction critical to absolutely every foundry environment, but the ability to link in properly accurate and measured equipment conditions. So with that, I think you can begin to see how the majority of the elements associated with Industry 4.0 can be achieved using aluminium die casting and the digital twin techniques. I'd just like to really close now in terms of the further advantages that I see for digitalisation and our industry. In terms of our industry, we have the best in terms of world-class academic institutions who are specialising in the liquid metal processes. And then there's also a whole raft of global professionals who sit underneath that academic structure that we have within the UK. Our industry, not just talking about aluminium now, but going back further to other materials, we've operated the absolute blueprint for the circular economy for over 3,000 years. And everything the other industries want to try to achieve in terms of sustainability and say the circular economy, it's something that our industry does and has always done throughout its whole lifetime. I personally do believe that for the organisations within the UK, those who adopt this sort of level of innovation, the technologies, and probably focus more towards niche volume, higher value markets, have a great ability to maintain a competitive advantage for all of our industry sector. And my final point is in terms of promotion and education. If we can get this message out in terms of how our industry is adopting digitalisation, how we really need to adopt digitalisation within our industry, I think it could be a really, really good draw in terms of recruitment and development of our younger people and really promoting academic excellence, which then all of us in terms of members of our industries could benefit from. So that's just a summary of where I believe we could benefit in terms of the whole process itself. That is all of my slides for this evening. I would be more than happy to share if anybody needed any further information or wanted to get connected with the businesses which I've referenced within the presentations as well.
Thank you very much.
Brings me in on half an hour, Pam. I think that was the plan.
That's pretty good. Well done. Yeah, thank you very much. And so well done. A very interesting presentation. Clearly, it's. I mean, I think it's sort of a bit mind-boggling. I think to people who are not familiar with it. And I mean, do you think there are barriers to entry for companies, or is there good help out there for companies who want to get involved in this type of technology?
Yeah, there will be barriers. Obviously, I personally don't think cost is the main barrier. I think having the skill level within the organisation is probably more of a barrier than the cost barrier. But I would always say that those the academic institutions around us normally are able to provide the solutions, or a potential solution to that barrier as well.
Yeah. What about IT? I mean, what about things like bandwidth? And I mean, it's presumably quite heavy on energy from a sort of an IT perspective.
It
Oh,
is.
sorry. Yeah, sorry, I thought I lost you there. Sorry, you moved around on my screen for some reason. I think probably because Mark put his hand up. But yeah, carry on. I lost you for a minute there. Do carry on.
Do you want to take Mark's question first, or
No,
do
you
you?
carry on. You answer my question
Yeah,
first, then we'll
yeah.
come to Mark. Thank you.
At this moment in time, there is a big discussion regarding AI, and the environmental impact associated with AI, based around the data centers which
Yeah.
are going to be needed to store all of this new data that we need to create.
Mm.
I just hope, that, as everything within IT, then we don't have to. We can develop our processes, but we don't have to keep providing a burden in terms of the environmental impact for these data
Yeah,
centers.
yeah. Well, certainly, I know some of the data centers, the Amazons of this world, are starting to invest in their own energy generation systems, aren't they, to try and counteract the sustainably generating as well. But
Yeah.
Mark, we come to you. You have a question.
Yeah, I mean, I'll comment to the last one as well. We have done some work on data centers. I mean, it's not just the storage, it's the uploading and the downloading that also takes energy, and they take different amounts of energy. And we now in the UK, the energy of data and data centers, whatever type of data you're talking about, we have as much energy going into those as we do in manufacturing. So it is a massive, massive amount of energy. But of course, that's all electrical energy. Very little of it is fossil fuel energy. So as long as the electricity is made from renewables and sustainable electricity, it's less of a challenge. But of course, you do have the network challenge, and the fact that you have this, what they call a rebound effect, that we might have to increase our capability and therefore increase our materials usage, which I think is a big challenge for everybody. But I might talk about something like that on when I do my Whitechapel lecture in April. Now, my question actually to Tony was, you've got there were a couple of points. So firstly, you didn't touch very much on, you talked a little bit about sustainability, but I think, digital twins and the digitization has a massive impact potentially on sustainability. You may want to make some comments there. And my other comment is cybersecurity. We're bearing in mind our geopolitical issues there are at the moment, with things like AI technology, machine learning, additive manufacturing technologies, any material technologies now come under export control from the UK from the 1st of April 2023. Anybody who exports anything to do with AI, anything to do with control of additive manufacturing systems in metallic systems, they all come under export control. We have to be really, really careful about those aspects. But here we are, potentially opening up our manufacturing processes to global potential of cyber attack. What are the issues with cybersecurity, and what have you worked in this area? I mean, we ran an MSc on cyber secure manufacturing, which we started probably 10 years ago. You know what? We didn't get any students on it. People weren't interested. We were probably too early in the game. But I mean, is that something that is important for your company, or you see it in the companies you work with, Tony?
We've come back to the first point, Mark, in terms of the sustainability. The biggest challenge where I was asked to talk about digitalisation within our industry was how do I hone it down to any particular area or concept.
Yeah.
I did think about trying to do a spread about digitalisation in all aspects. So yeah, you are right. Sustainability didn't come through in terms of that, but I think yourself. I personally believe that our industry, when managed correctly, is the most sustainable manufacturing possibility that we have to us. in terms of the cybersecurity, I think it's absolutely fair to say I've shared information provided through Beulah. Beulah are very, very aware of the concerns, but I think that it is still at the awareness stage as opposed to the definitive, we have it under control stage at this moment in time.
I mean, what we don't want to end up having is what happened in the NHS in various trusts recently, where they got, basically attacked, hacked, and blackmailed, let's say, otherwise patients' data was not going to be released. And we don't want our manufacturing systems, our manufacturing companies to be held to ransom, essentially, or potentially deliberately sabotaged. The process could be deliberately sabotaged to create something that you're not aware of that then ends up in some sort of failure. That is, for me, a big concern. Suppose a wrong un, an actor that we don't really want to be involved in our manufacturing process introduces something that we don't know about that ends up then being a safety critical component. We really have to take this on board very seriously. And I think I agree with you, Tony. It's something that, especially the smaller companies, are really not up to speed on. Even the bigger companies like Beulah are not up to speed on. Definitely. And I don't know quite how we address that, but it's something we need to start. We need to somehow start that discussion at a very, very at a national level, because I don't even think the government understands that properly in manufacturing. They may understand it in what they generally call as information systems and defence and things like that, but not in the rest of the stuff that we get we deal with.
Okay, thank you. Any other questions? I was going to ask you, Anthony, do you think there's anything in casting that it wouldn't apply to? You focused on high pressure die casting, particularly for automotive sector. And that's really Tesla have come in as real disruptors here, because they're proposing a solution which would have been considered quite radical, probably even 5 or certainly 10 years ago, in terms of reducing the number of parts. And people worry about, you've got like 3 castings replacing loads of castings, and obviously if that part is incorrect in some way, you've got a lot of scrappage in a way. But as you say, it's disruptive because it's going to be close coupled to the assembly plants.
Yes, yeah.
But that's a whole other question. But in terms of areas where it's not applicable, do you think there are? I mean, there are anywhere where it might not be suitable for use?
It's always scalable, isn't it? Yeah, as I said, there is a completely different discussion regarding one-piece castings for automotive, and are they to the purists in terms of die casting, sound castings? Maybe, but I think as an industry we do have to recognise that they might not be what we think is a perfect solution, but they deliver exactly what that customer is trying to achieve. So in terms of their principles, they are correct. I don't obviously that level of digital twinning isn't going to roll down across every part of our manufacturing processes, but I do think it's really important for absolutely everybody associated, not only in terms of die casting, but also in terms of non-permanent molds as well, in terms of data capture, data analysis, and prediction of what the manufacturing process will deliver, as opposed to just the old technique of measuring the output as opposed to controlling the inputs.
Alan, you want to ask a question?
Yeah, just it's maybe a rather ignorant one, really, but at the start of your talk, which I greatly enjoyed, Anthony, you compared this process to creating a design to the traditional continual iteration method.
Yeah.
Is there any comparison between what, if you like, the AI-driven system produces as an object to be cast, as opposed to how the object would look if it had been produced or designed through the iteration sort of process? Or is that an irrelevant question because you couldn't actually reach the complexity and size of some of the things you're looking to do now if you did it by that traditional method? I'm just intrigued as to how the new compares with the old, or whether they're just non-comparable.
I'm not sure if they are comparable, Alan, and I think one of the reasons why they're not comparable is this advancement in terms of topology designs. Topology has been around, I'm not sure for how long, but for an awful long period of time. But it's just never been accepted within industry because there wasn't the processes available to manufacture to those designs. The onset of 3D printing has really opened up the eyes for everybody associated with topological designs, and I think we're all just trying to catch up with what 3D printing can do. Obviously, sand casting can do it every single time, but we're now in that position of okay, but with volumes, how can you get permanent molds, dies to be able to deliver the same? I'm absolutely convinced, Alan, that the conventional method would have always got to the end point. I just think there is a challenge that the conventional method of doing things does recognise the speed advantage for doing it in the CAE space.
Okay, because you mentioned printing there, 3D printing, because I would have thought, coming back to Mark's point about information protection, or that 3D printing has already had to address that very much. So I'd have thought in having this ability to have your printing machine sort of anywhere in the world, it may be close to the customer, but keeping the design centralized at, say, a Rolls-Royce or such. Like, so I mean, that aspect, Mark, must be something which is already in the thinking of some sort of industries and production lines.
Yeah, well, that may be a question you need to ask Philo Martinez, who's going to be presenting on the 3rd of February. He's running a company that is a spin out from Cranfield called WAM 3D, and that's the sort of question you should be asking him, because WAM 3D is selling technology, and they're selling process control technology to be able to make components in the wire arc additive manufactured world, not wire arc, I mean additive manufacturing, which is much more sustainable than powder bed, because most of the material goes into the component rather than having to be recycled, remelted, reblown. And the production of the wire that you use in the first place is much more sustainable, or rather, you get higher yields. So it's a more sustainable process, but it's for big components, or large scale, not little ones. I think the security aspects of designs is something that maybe he might have a comment on. I think there is a challenge with additive manufacturing, because, as I say, it's only 18 months ago come into the realms of export control. Additive manufacturing specifically for metallic components, because of the high defense related aspects of such components, because it's obviously got potential really huge benefits for component manufacture on the field, in I'm sorry to say in war in battle situations, as it were. So a replacement of components by printing them straight away, rather than having long supply chains and stock of components for replacement. And I think that's why people like DSTL have been really forcing the government to change the law on export control for materials technology for additive manufacturing, and also process technology of additive manufacturing for metals, because they see it as a fundamental aspect of something for the defence in the future. Sorry, we've gone a bit off piste here, but
thank you. Yeah,
but it's still related to the digital twins, because the digital twins have to exist for all these components to be additively manufactured.
It's the same. It's the same issue of protecting data.
Yeah, absolutely, it is. Absolutely, it is. Yeah.
It is. Yeah,
and that becomes a bit. It becomes a much more challenging part when you realise that where our data goes. Which servers did it go to? Does it get stored on the cloud? Where does it get stored? Where are those computers that are storing the data, and who has access to them actually? And are they in some remote place in Iceland, or are they in some remote place in Siberia?
It'll be funny. We'll end up going back to servers sitting in buildings, won't we? Where it's the only way
to that's right.
They're not allowed
to be connected. Allowed to be connected to the outside world. Yeah.
Anybody from the foundries want to ask any questions before we sort of wrap up? Just conscious of time.
Hi, Simon's got a question.
Well, it's not a question. It's just I knew nothing about this, and I'm very impressed, and I've learned a lot. And thank you very much indeed. You guys are talking about things way above my head, but I just want to say thank you very much, because I found it very, very interesting.
Good. Well, hopefully, it's teed it up nicely for the February talk as well. Well, if no one else has got it, John, you wanted to say something. Do you want to unmute yourself as well, then, John? John, you're muted, I think.
Am I muted?
Well, there's two Johns. I mean, John Campbell is trying to speak, but is muted. John's iPhone, I think John on the iPhone. Is that you, John Wood?
No, it's John Swift. Yeah.
Okay. Hello, John. Do you want to say something then? And then we'll come to John Campbell.
Oh, me? Okay.
Hold on, John. I'll come to you in a second. Just let's go to John first, and then you hang fire. Yeah, John Swift?
Yeah, sorry, I can't get my camera working. You know what I mean?
That's typical iPhone.
Yeah. Well, that's the problem. Anthony, just a question in reference to the CAE, and you gave a wonderful example from Bionic Edge Limited about how quickly you could design a complex component. But is your view that the foundries will be the people that will be really generating the components for the automotive industry, or will it be in collaboration together?
Oh, good question.
I think initially it will be the people leading the designs. I think it's imperative on all of us to make sure that we are the incumbents in terms of the design. There is an issue that quite easily that CAE sole method of modeling is just relying on historic casting simulations. So again, it could end up leading towards this design harmonization. But I think probably looking at the UK manufacturing, John, I think it's just really important that all of us recognise that there's a further change coming down the tracks, and to be aware of it and to take it on board and to absorb it. Bionic Mesh are a small company, but they really are doing things differently, and particularly making an impact in terms of the UK automotive base as well, and they're very keen to work with suppliers of factual casting simulation data to feed into their algorithms all the time.
I guess there is a difference between optimizing design per se and optimizing design for casting. And they're not necessarily the same, are they? And it's the garbage in, garbage out syndrome. I mean, that's a bit crude, but you know what I mean. It's the same sort of idea that you've got to design for manufacture as well, haven't you? John, thank you, John, for your question. John,
you can start off with optimizing for stresses and underloadings.
Yeah.
And I think rather than that may not be on old designs, that may be very new. And I think that's
new
where
designs,
I think
you
that's
can
where
you can optimize them, put the material where you need it, can't you?
Exactly.
Exactly.
So they become more organic. Yeah.
So John, I know you've been waiting. John Campbell, Professor John, do you want to jump in there?
I'd just like to pick up a point just very briefly made by Anthony when he said, there is sand casting. And I'd like to emphasize those processes, particularly sand casting when it's done well, in that you don't need to worry about a digital twin for the filling of the sand casting if it's been designed properly, because physics takes over. And in fact, it fills according to the laws of nature, and it's totally passive and needs no input from anyone. And so in contrast, of course, to pressure die casting, which is, needs a lot of input and a lot of control, and is frankly very difficult to control. So I mean, it's not surprising that we have to put a lot of effort into the monitoring and attempts at control. And even now, the quality isn't all that we would like.
I think, thank you, John. I think that's probably a topic for a whole other debate, and we could have a heated debate, couldn't we? Which is best, die casting or sand casting? Discussed, and that would be a whole other session. But I'm conscious of time. It's 8 o'clock now. Thank you very much for everybody who's joined this evening. Thank you for the questions. I hope you found it interesting. I'd like to thank Anthony for taking the time both to prepare and actually to present to us. So thank you very much. Yes, a sort of a silent hand clap you're getting from everybody, Anthony, and much appreciation. And thank you very much, everybody. And I wish you good night.
Yes, good night.
Thank you,
everybody.
Thank you.